I'm pretty excited about today's class. It is a topic that brings together a lot of aspects of my own practice, and even the kind of course image which is displayed here is really the focus of today's class. Uh, that's kind of like in the extreme case of what we're going to build today, but today we're really going to be focusing on the capacity for neural networks to serve as sort of general feature extractors and really look at what happens when we take a large archive of, could be images. We'll see examples of audio, and the visual that you see here is actually an audio archive. But what happens when we take a large media archive and we apply neural networks to it to try and extract out some structure in that archive? And that structure we're going to call a manifold. So today we're really going to walk through some of the steps that get us there and look at some of the popular techniques when applied to images of how to create an image manifold of a large image data set using neural networks. So a little bit of background first. So what is a neural network? We've kind of skirted this issue a bit. You know, we had a bit in the intro session, but let's dig in a little bit more. Like, there's still a lot more to understand with neural networks in terms of the maths, and that's definitely beyond the scope of this course, but let's try and build some intuition for what is the neural network doing. So I found a couple of resources online that I think do a good job, and they all more or less work with this image data set, which is known as MNIST. It's a subset of this really large data set by the National Institute of Science and Technology, maybe something like that. And they had basically people fill in forms. These were digitized and scanned, and each letterbox was detected and put into this large database. And a subset of that database is just the numbers. So just the numbers 0, 1, 2, all the way up to 9. And it's a really popular image data set. There's about, I think, 60,000 images of these numbers. So what happens when you look at that image as a neural network and try to then predict what is the number that's being represented by that image? So let's take a look at this video. Let's see. Then hopefully the audio will come through okay. Let me just double check that I can't share my audio directly to Zoom.
Told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this and outputs a single number between 0 and 10, telling you what it thinks the digit is. Well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits.
Okay, so this brilliant series by Grant, I forget his full name, but the 3 Blue 1 Brown series, he tackles a lot of really interesting mathematical concepts. I think this does a really nice idea of illustrating the fact that an image is just a series of numbers. And what's going on in this first image is that these are all pixels here. This image of a 7, there's 784 pixels. And so that's why you see these circles. These circles just represent containers for numbers. And the edges here are, how are we going to multiply those numbers to produce a new number? So there's a set of weighted edges connecting every single pixel into another representation, which we'll call a hidden layer. And we're going to do that a number of times until at some point we've transformed the representation that was pixels into the representation that says that's the number 7. So on this last layer here, there are 10 numbers, and it's not, the final layer's representation is supposed to be something like a probability. So this number will be scaled from 0 to 1. And we'll see that later in the lab as well. But are there any questions on this kind of first layer representation of an image all the way up to this last layer? Like anything that you want to throw at me, ask me, let me know. We'll look at some other images and videos as well after this. But the basic intuition of multiplying pixels into a hidden layer. This is a hidden layer. That's kind of what's happening. I visualize it as a geometrical kind of like warping. Like, can I warp these pixels by stretching them, morphing them, and then putting them into 10 different buckets somehow based on mathematical operations? So later in the video, he describes some more intuition for what the network might be learning. So just here, for instance, you have basically a network that is initialized with random weights. So these green values represent positive values, and the red values represent negative values. So back on this image here, all of these edges here are represented by these red and green pixels later here. And what it's saying is, how can I weight all of these pixels into one value of my hidden layer? So if I've got the number 7, I might want to look for strong edges on the top, and on strong edges on the top of that part of the 7. This one node of a hidden layer is basically composed of all of these randomly initialized values multiplied by that number of a 7, and that will lead to some other random value, right? On the right here, we have a supposed image. So this could be an image of a 7. Grant's showing here like the top bar of the 7, what happens when you multiply these random numbers with the top bar of the 7. You would get a really high activation. So let's say instead of that random number of random image of lots of different numbers, we're going to have high weights here where there's green, and then low weights where there's red. What happens now when I multiply these edges, these weights, by an image of a 7 is that I would get a really, really high value whenever I saw anything that looked like this part of the 7. And it wouldn't respond to anything else. It'll just cancel out any activations for the rest of this image. So this is just one small video, and it's there's a lot more out there, but I found this one pretty helpful. Dig into it if you want to learn a bit more. This is heavy stuff, so I don't expect everyone to gain like a master understanding of
figure it out itself using machine learning.
This is another video. This is from Google AI Experiments, and it again works with that same data set and tries to show that each pixel is effectively a numeric representation. There's 784 pixels, just like in Grant's video.
The image is 784 pixels. The computer treats each pixel as a dimension. Again, using t-SNE.
And so they jump into this other visualization, which we're going to explore today. But it's trying to represent what a neural network does in order to organize these images, what it learns first, how it learns to separate and build representations that resemble those strong edges, for instance, like where it expects to see a 7, or a strong edge where it expects to see a 1. What do you think, after having done the mean and standard deviation exercise, what do you think is the first thing that a neural network would sort of pick out? Like, what is the mean, let's say, of the MNIST data set? If you were to take all the numbers and average them, what do you think would be learned just by that basic representation? It would kind of look like an amorphous blob. It might even look like the number 8, right? Like, so you have like most of the numbers covered by the number 8. Parts of the number 8 would be additionally covered in. So a neural network might try to first pick out this general shape of where it expects to see most of the information, where all the edges are. And then it might learn to distinguish between each of the numbers, what separates each of the individual numbers. That's just some intuition on what's happening with a neural network. So more complex neural networks might try to work with actual, very different types of information. We've been focusing on images just because they're easy for us to work on in terms of data, like we can get access to that. But you can work with any kind of input space, so these 784 pixel values could be 12 numbers representing some class statistics, or they could be the values of an audio waveform, or really anything that you can imagine could be input into this and then taught in the same way that this neural network was taught. So this is another video by Fernando Villegas is going to speak in a moment about neural networks. I found this one also quite interesting.
And so today we're going to talk about neural nets, and one of the things that sets that apart from the kind of old world computing that Martin was talking about is the fact that these systems learn over time, right? And they're modeled after the human brain and nervous system. They're also probabilistic. So there are many things, there are many sort of shades of gray there, no pun intended. And they're not predictable, they're not completely predictable. And that makes it for a really interesting opportunity for visualization, because one of the big challenges is understanding exactly what is being learned by these systems. And experts don't always know what these systems are learning. So this is a very simple sort of artistic rendering of what a neural net might look like.
Yeah, I'll let her continue, but just to kind of go back to this previous part of the animation. So we saw with MNIST, for instance, that the first layer might try to pick out the overall shape, for instance, just based on our previous exercises with the mean. Like, that's generally what I would expect the first layer to pick out. In order to pick out that general shape of the image, one way to think of that is that it's learning edges. It's what a lot of like human visual cognition might call like a low-level visual feature. And they call it that because it's represented really in our own brains in early visual cortices. In the first of 6 layers of visual cortices, you'll find things that look like edge detectors. And they basically, an edge detector, and like what this little image here is trying to represent, is that if it finds a really high value and then right next to that there's a really small value, it will weight the contribution of all of those pixels and it will respond highly. So it's an edge detector because it's looking for a pattern that resembles what you see here. Whenever there's a high value, it'll multiply a pixel where there's a high value. And if it finds a low value next to that, it's going to add that negative contribution positively. So it's basically responding to whenever it sees a pattern like that, and it's going to, the overall contribution will be a very high value. So if you imagine that each pixel here is an edge here, and each of these dots here represents a part of this image here, then what you're seeing here is what happens when I weight my pixels in a small region that way. I will get a high value here. This is a pretty low level explanation of neural networks, but I wanted to try and give you some intuition on that. But I appreciate that's pretty strange information. Are there any questions about this? Any questions anyone have? All right, well, I'll continue then. Let's see. There's another article by the StillPub. Have a look at all of these as well in your own time, and I think they're pretty helpful. So this is again on MNIST. This is showing kind of the process of learning of a neural network over time, how it learns to separate images slowly over time. And if you continue in the article as well, you'll kind of see a type of neural network, what its representations might learn in different layers, resulting in the final layer of the prediction of what the number is that's represented here. Okay, and they go on to talk a bit about dimensionality reduction, which is what we're going to play with in this class later today. So we have here in one of the middle layers here some representation, like this means nothing to me, but to a neural network somehow this set of numbers represents mostly the probability that there's a number 3. Very small amount of numbers compared to the 784 numbers here. This is maybe 100 or so numbers, or 50. Yeah, this is 50 numbers. So somehow this neural network has learned to compactly represent any image that looks like its training data, which, you know, this set of data. It's somehow learned to compactly represent that into a set of numbers. We call that like its internal or hidden representation. We're going to be playing with how do we interpret this internal representation? How do we get some more information out of that and build structure out of it? So before we jump into that, I'll show you a couple examples of this. So this is a video showing the process of learning the same MNIST data set and a visualization not unlike this one, but also another type of network here on the left, which is actually learning to generate the same images. And what I want you to focus on is what is it that the neural network learns first, and what is it that it slowly learns to figure out over time. Each of the colored regions here on the right represent a different digit in this sort of reduced down space. So here to begin with, there's really no class separation. The neural network has no idea what the difference is between a 0 or 1. And here on the left, you can kind of see, well, how has it learned to interpret every image? It thinks that every image is basically this amorphous blob, right? Like a 1, a 2, it's all kind of in there, but it still hasn't quite teased out the differences. So we let the neural network continue to learn a bit more. It's increased its variance, so it somehow learned another axis of representation already, and it's, you know, it wasn't as densely compact as it was here, right? Like here it was just like every single image was really the same. Here there's still some variance, like there's a lot more variance here, but it still hasn't quite figured out the class labels. And then here it's starting to figure out 0 versus 1. So this blue region must be 1. And then everything else here is probably every other digit. We've got now 0 here, really clearly pronounced, and the rest of the digits in the middle. And you can see that here in the generation of the images. Maybe it's got some 9s here. And sort of towards the end, it's learned a couple of the digits. It's got 6 here, it's got a 9, it's got definitely lots of different angles of 1s. Maybe it'll soon pick out the difference between a 9 and a 7 here. That's just kind of a fun visualization, I think, which helps show this process of learning and how it kind of slowly adapts to different information. So have a look at some of these videos if you want to gain more intuition on what's happening inside neural networks. I found that these were fairly good. This OpenViz conference talk is actually quite long, and they go on to talk about quite interesting things. I really like that video. Okay, so I mentioned this idea of feature extraction, and looking at this image here, for instance, this is meant to be a neural network being drawn here, where at some point it learns to predict a horse. And I mentioned with the MNIST network, as well as this network, like the layer just before the last layer, you know, this layer here is actually quite interesting. And it's often used as a feature extractor. So that's what we're going to focus on next, is really like, what does that mean? What's happening? Well, in human vision, we already have this idea of extracting features. Like we have a very active role when we look at the world. We have a retina. It's a really weird thing that it moves 3 to 4 times a second. It does that in order to see really high spatial frequency information, and outside of the focus of what it's looking at is very low frequency information. It's almost like your mean images, right? It's like very low spatial frequency information, meaning that the edges are very coarse. It's the gist in another way to think about this that we saw last week. So for some reason, our visual system has adapted to generally always have the gist of a scene outside of the point of fixation. But then at the point of fixation, there's a lot of high spatial frequency information. There's a lot of detail there. And so why would it try to do that? Well, if we consider different layers of processing, one way to think of this is that you have, at the lowest level possible description, you have pixels. If you think of more, what would be the next level of representation in our visual cortex, as well as in computer vision systems, it is some sort of feature. It could be an edge, it could be a corner, it could be the contrast of different colors. So like the difference between a blue and a yellow, or a red and a green, for instance, like a very strong color contrast. That's another type of edge. These are basically types of features that system generally end up learning in its first layers. And as you go up to the next layers, what you'll generally find are groupings of those features. So something like an entire whisker, or part of the eye, or part of the nose. And then finally, towards the last layer, you have most of the scene covered. You have this high-level description that might represent the entire face, or even the contrast of the tiger in a jungle, like that high level of a representation. So early visual computer systems tried to model that by directly extracting the features. They would essentially try to find these features, and they called them key points. And they thought that they were really detectable and almost like repeatable out there in the world. Like no matter what angle you looked at it, you would find those same key points. And so early visual systems were able to computer vision systems were able to do really remarkable things like panoramas, which you see here, or build entire structure out of multiple views of the same scene. And you might know these as point clouds. And you can get these things on your phone now. Like you just walk around and you'll see those points build up an entire representation of a scene. Those points are essentially built up out of these really low-level features, right? What does it look like? What do some of these features look like? So here you have a visual RGB image. Here you have a luminance representation of that same image represented in grayscale. And then here you have two types of color opponency representations of that same image. So there are contrasts here between, the hair and the face. Here there's a different type of contrast. Wherever you might find corners or edges in this image, that's really one set of representations that an early layer of a computer vision system would find. This is just kind of describing how to create an edge detector and what that might look like. So if you were to apply different types of edge detectors to the same image, these are where you'd find responses. You'd find, for an edge detector oriented at 0 degrees, for an edge detector oriented at 45 degrees, 90 degrees, and then 135 degrees. So somehow a neural network has learned to define all of these different types of edge detectors, both in different orientations, in different color channels, and it's learned that based on the data that it was given. It adapts its features that it's extracting based on the data that it was trained with. And it often just ends up looking like the things that we know to have in our own visual cortices, which is just really fascinating and interesting. Yeah, so these are just some more features, basically. I won't go into it any more than that. And we saw this image in the first week's lecture, kind of similar idea here, where we have some input image. These are all going to be the different pixel values of that input image. Really, that means nothing to anyone if you just kind of look at that set of pixel values. But somehow, if we weight all of those pixel values, we'll get different sets of feature responses to different edges. So each of these edges are essentially different feature extractors. They are these different oriented edges. And the responses here are where those edges were found. So essentially, the key points of that image. we get farther and farther into the network, and we get more advanced and coarser scale features, until finally you get something that is whatever that task of that network was for, like to identify who was in that image, for instance. But this second to last layer is really, really fascinating because it somehow encompasses all of the features of that image. It has so much information about that image at a semantic level. It's really somehow encompasses a lot of detail about that image. We'll see next week as well another way of kind of trying to understand what are the representations in each of these layers, and like what do they mean? Like how did the neural network ever even learn them? But what do they look like? And we'll do that using a technique called deep dream. But for now, just to get an intuition of what each layer might be learning and representing, this is another way of thinking about it. You might have an image composed of many different types of edges, and these might be the responses of the most predominant edges in that image, for instance. And then going up to the next layer of representation, there might be textures and groupings of different edges that resemble patterns, essentially, to more complex patterns, to even parts of objects, to the whole objects themselves. All the weights are more or less random. And then slowly it learns, like in the case of this video, it learns that there might be strong edges around the difference between a 0 and 1. And it'll try to find the weights that define the difference between those two. And you do this by giving it, so in this data set, there's like 60,000 images, right? So you give it some images at a time, and you try to give it a balanced set of images. So if there are 10 types of classes, you'll try to always maintain the number of images that you give it so that it represents all 10 classes. Like you might give it 10 images at a time. And it'll say, well, in order to better predict the difference between 0, 1, 2, 3, all the way up to 9, I had to adjust my edges slightly so that it looked more like the difference, so that it looked more like, rather than this random image, it looks more like this one here. That might be one of the updates that it learns. But in general, the updates that it learns are really, really complex and strange and crazy. And it's very, very hard to interpret those. But at some basic level, it's learning incrementally to update in each layer, whatever that layer represents. Like in the early layer, it's learning to represent its edges better. So we're going to move on a little now away from this idea of what the neural network is doing and look more at what we can do with that neural network. So there's been a pretty fascinating 10 years or so work on a really popular technique called T-SNE. And we'll look at what that is. It stands for T stochastic neighbor embedding. And I honestly can't tell you how it works, but what it's trying to do is take a large number and represent that large number with a smaller set of numbers. So if I've got a set of images, I've used a neural network to extract this final layer of representation that somehow encodes interesting bits of that neural network in it. So I've got, let's say, this layer for my MNIST images, or for a more complex neural network, I've got whatever this layer is representing, some core set of features that represent all the features of an image. I extract this layer of information for all of my images. I will have, let's say that this layer was 2,000 values, and I've got 100 images. So I've got now 2,000 values for each of my 100 images. And I want to know, how can I organize these images in a way that the distances in that 2,000 dimensional space are preserved if I look at it in a lower two-dimensional space. It's like if I gave you 100 images and I said, now organize these on a 2D grid so that the differences between each image are preserved in a way that this neural network thinks that they're different. So if there's 20 images of horses, I would expect to see them closer together because this neural network was trained to think that horses should be more or less the same. And then if I saw deers, they might go into another cluster, and planes, they would go into another cluster. So we'll kind of look at that through code later today, just giving you the high level now. So some artists and educators have looked at this process. Lev Manovich has looked at this. He was at UCSD when he was looking at this, and this was a large archive of different comics, and pretty interesting study. He worked on what he calls cultural analytics, and was really using it to understand the archive. It wasn't just like a visual aesthetic process that he was exploring. It was really like a Scott McCloud understanding comics type of exercise. Like, what are the rules that are used for different types of comic authors? How do they relate to each other? Are there certain aesthetics shared by different authors? Can we learn that purely from something like a neural network that have some representations that it's learned somehow? Can we learn what it means to be a similar comic from what a neural network thinks is similar? You don't just have to apply this technique to images, right? So there are neural networks for literally every type of digital media. So I've looked at this with a audio archive. So each point here represents an audio segment rather than an image. And the idea is to project this large archive of audio into a space where you can explore the audio, where the distances between points now represent similar sounding points rather than just a file browser of audio files. Like, how do I organize that? How do I understand what's in a large archive of audio? So this is a really interesting use case because at the time, this was like 2010 or so, there was a large archive of audio recordings that nobody knew what was in these. There were 60 hours of digitized tape reels. And, you know, there's really no way to look at that other than 1.wav, 2.wav, 3.wav, and each one is an hour long. How do you grapple with that amount of data? So this was an interesting exercise, and this used basically just a way of looking at all of that data through this dimensionality reduction idea. One of the most fascinating works of art that I've ever come across that explores this idea is Archive Dreaming by Rifik Anadol. And so you can explore a bit on his Vimeo of this work, what he's done. So he's, from my perspective, I think that he's taking this whole narrative of what it means to use something like a neural network to ingest an archive and he's really explored every single stage and built a really comprehensible narrative of what it means for a neural network or a machine to think about an archive. And this was one of his earliest works, really playing on that theme. This was an archive in Istanbul. So I really love this visualization that Rafik has built here with the Salt archive. He's showing, he worked with the artist Mike Tyka at Google, and Mike worked with a neural network to extract features from each of these images. And what he then did was take all of those features and then project them, the high dimensional features, which would have been something like 2000 values. So for each of the images in this archive, he had 2000 values. And what he wanted to do was organize that image archive into a 3-dimensional space rather than a 2000 dimensional space, which is like, I don't know what that means. I don't know how to interpret that or visualize that, but compactly represent those 2000 dimensions in 3 dimensions. That's what t-SNE allows you to do. It's one method of doing that. PCA is another, and UMAP is another. There are many ways, but we'll be looking at them in the lab. And then he goes on to look at these perplexity experiments, which are, it's basically a parameter of t-SNE, and leads to very different types of dimensionality reductions. So you can actually, with the same algorithm, explore many different ways of organizing that 2000 dimensional space into a 3 or 2-dimensional space, or whatever dimensions you want, really. You can go from 2000 to 1000, but you still don't know what to do with 1000 dimensions. Maybe you have a process that allows you to work with 1000 dimensions, but we'll be looking at 2 dimensions today. So it's quite cool. I really like this work. Definitely was like mind-boggling how much information and just how beautifully visually represented everything was. And then I got the opportunity to work with Rafik the next year in 2018, and worked on both the audio and image archive of the LA Phil. And that was like a 40-some terabyte archive. And so much like the Daphne Oram archive, you know, just kind of much more data. And, you know, a couple years later, thinking about how to organize, in this case, this was like 7 terabytes of audio, and then there were like 20-some terabytes of images. How do you project all of that information from the LA Phil, 100 years of audio recordings, into a 3-dimensional space where distances are still preserved based on that high dimensional feature? This is just a short playthrough of the space. There's some audio in this. No, there's not. This is just fun. You can look more on his website for how that was projected on the Walt Disney Concert Hall and made into a 12-minute something piece. And there's some visuals as well on the website, kind of loosely trying to describe this. So there are 500,000 photos. There's a neural network. We'll take the second to last layer of the neural network and interpret that high dimensional feature into a 3-dimensional feature using t-SNE. Same idea with audio, using an RNN and then projecting that down, again using something like t-SNE. So there's been some related work as well on using the same sort of techniques where you have an image neural network, you look at the different layers, features, you project that to, in this case, 2 dimensions instead of 3, You try to understand if that can help you explore any aspects of art history, for instance. So there's a lot of work done here. There's also, I think I have in my notes here, presenter notes. Yeah, C. Richard Johnson of Cornell University. Also worth mentioning, if this interests you at all, has looked at lots of different features of different paintings using different scanning techniques. And it was like a 10-year funded project or so. And I imagine that they would be thrilled to work with somebody that could try to understand their image archive using some of these techniques. Okay, last-ish but not least, we have these experiments from Google. These have been done in the last year or two or so. There are some that use images and some that use sound data. So these two are examples of audio archives, and then there's some that are image archives. This is most of, or some subset of Google Arts and Culture's archive. And then these two I want to point out because we're going to look at one of the interesting techniques that they used. So we saw with T-SNE so far that the images were kind of in this weird amorphous shape, like even the image here, like this structure is created by that dimensionality reduction algorithm. But what if you wanted to project it to a known structure? Like in this case, there's a grid, and you wanted to map each of these points to the nearest point on a grid. So that's a technique or a problem, let's say, known as the assignment problem. And there are many ways of solving that problem. You can, you can even imagine taking this set of points and mapping it to a 3D model's points, like a model of a person or an object or whatever you want. That's the same technique, the same problem, known as the assignment problem. And we'll be looking at how to do that. So I'll skip the last bit, but have a look at these. These are more recent works of Rafiq's, and he's actually got this latent image browser, which allows him to explore that T-SNE cloud, but also at the same time look at the rendering of the GAN represented by that point in space. It was really cool work. Cool. So this, I'll be copying again, like I did last week, from a notebook that I've already completed, and I'll share that with you at the end of class. So we'll be working on this idea that we've seen so far of taking a neural network, extracting features, and then learning a manifold from that set of features. What we're going to try to understand in stages is how we first use a neural network just for classification, then how we would extract features from that neural network, how we would use this technique, like we mentioned, T-SNE, to reduce those features in its high dimensional space, excuse me, to a low dimensional space. We'll then look at visualizing an image data set using that reduced down space. And then we'll look at this assignment problem for how we can use the T-SNE space, which can be quite amorphous, and try to map that to a known set of points. So if we wanted our organization of images to look like a grid, we could map the T-SNE points to a grid. If we had another set of points, we could also do that. And then along the way, we'll also look at how to work with really large data sets of images. Okay, so lots to get through. All right, so as a kind of recap, just to kind of solidify last week a little bit, this might be ambitious to try and do all of this, but last week we looked at an image data set and tried to calculate the mean and standard deviation of that data set. And what that represented was a point in space, the mean, as well as the standard deviation set up an axis. So if you add points to the mean represented by the standard deviation, you go on one side of this axis. And if you look at the negative standard deviation, you're looking at this other axis. So that's pretty interesting representation. And we'll be seeing what a neural network can learn with the many more axes of representations effectively. So last week I'm just kind of repeating the code from last week here. We looked at these imports, and then I had a function to download all these images. Okay, so this is the notebook. Hopefully everyone is able to view this as well on their own laptop if they want to copy and paste. But again, like last week, you'll get the full notebook. But do try and ask them questions if you don't, if something seems unclear. So I've just imported some libraries like we did last week and calling that same function to download the 100 images from this COLAB dataset. And I will load up all of those files here. And then for each file, I'm going to load the image, crop it, resize it, add it to my list, and then create a array out of all the images. So next, I'm going to calculate the mean and standard deviation. And I do that by averaging the 100 images. And we can take a look at what each look like. So this is the mean image. There's a lot of structure in this image. You can see that there's a lot of bias as well, like not well represented in terms of diversity, I would say, but this is an image data set, and what can we expect? Sure. There's a lot of deviation in the image as you go away from the face. So higher values are higher differences. Let's see. So we explored this one line of code where you could create many changes from the mean. So you could have the mean and then look at different amounts of standard deviation applied to that mean. So one way to visualize this is with a GIF. And take a look at what this GIF looks like. So I've done 100 images here between -3 and +3 standard deviations. Yeah, so here, this is a lin space, which basically means that I've created 100 values between -3 and 3. So the first value -3, and then so on and so on up until the value 3. And I've taken each of those values and I've multiplied my standard deviation image by that value and then added it to the mean. So what I'm trying to do is look at all deviations around the mean. The GIF will show each of the images that was created here by taking that mean and adding -3 times this image, and then adding the mean again, and then -2 times that image, and then again, and so on, 100 times up until you see 3 times that image. So what we're seeing here is this axis of representation created by the mean and standard deviation. So as we go from all the way from -3 standard deviations all the way up to +3 standard deviations, we're we're traversing most of the variation in the data set per pixel, trying to see what that means per pixel. Yeah, it looks like quite like smaller faces to larger faces. It somehow encompassed that change. It's also got like quite cold faces to more warmer faces, as well as some other changes in there. It's got most of the variation somehow collapsed down to one axis. If you recall from that, from this video, the first thing that a neural network learns is one axis of representation, essentially. And so the mean here is more or less that axis of representation. Some point source in here is a mean, and then along this axis is the standard deviation. All right, so let's move on to image classification. That'll be in the notebook as well. All of this text as well. So we've seen so far what a single axis of representation can represent, but we know that these neural networks are really high dimensional feature extractors. So let's take a look at actually using a neural network. We're going to be using Google's library called TensorFlow, and they come installed already on these COLABs, and you can just import it like that. And then there's this whole sub-library of TensorFlow called Keras. And it started as its own library and then eventually got merged into TensorFlow, and now it's just part of TensorFlow. And so you can access it by writing tf.keras, and it's a module, and there's a whole bunch of information on Keras. If you search for it, you'll see a website for Keras, and lots of code examples here that you could play with if you want. Different guides. Let's see, some code examples, for instance, like image classification from scratch. MNIST was that data set that we were looking at, how to download it and classify data on it. To more advanced things, working with text, for instance, getting data and building a model. Most of the tutorials will end up looking like this, and you'll get some accuracy on the data set, basically. The generative stuff is probably more fun and more applicable to what we'll be working with in this course, and we'll be looking at a couple of these. Let's see, that's pretty much, yeah. Text generation as well. So there's a whole example of generating text with Keras here. So it's the setup for that stuff in COLAB is really quite simple. You just write import TensorFlow as TF here, and you're good to go. So let's look at one of the image classification models called Inception. So there's inside of tf.keras, there's a whole set of applications. And so these are essentially all state-of-the-art image classification networks. And they can be used for other things as well, but generally they were developed for image classification. The one that we'll be looking at is called Inception v3. And we're just going to tell this network that we're not going to train it by setting net trainable to false. We're just going to be using this for forward inference. I actually don't know if this is necessary or not, but it can't hurt. So it's just downloaded this network for us. And in order for us to use this, we can actually just download an image, or however we want to work with an image. and provide it that image, essentially. So the purpose of this network is only really for for image classification, but we want to use it for feature extraction as well. So we have to do an extra step here, really. And inside of this network, there are a set of layers. If we try and look at all of the layers of this network, these are effectively the different columns that we always saw. Let's see here. These are these different layers here. They represent different activations of that neural network. Or back here, these are each individual layer of a neural network. Like, there are only 4 visualized here, but in fact, we're working with hundreds, really. So these are all different layers. So I think like 150 some layers or something like that. And so each of these layers also has a name, and we can grab one of the layers, for instance, like layer 0 equals the 0th element here. And then we ask for layer 0's name. And it says that the name is input 1. So what we want to do is get the name of the layer that represents the feature extractor that we want. And we're going to use that to create a new neural network that just has those layers that we specify as outputs. If we use this neural network, we'll only get the predictions and we won't get the features as well. So we have to just do this extra step, really. Let's see, so we're going to ask for the layers that represent the features that we want. And this last layer is the prediction layer, whereas the second to last layer is the feature extraction, the features that we want to extract. It's up to us, really. Like, we could pick any of these as features, some of the early layers might have more edge features. Some of the middle layers might be more about textures. So depending on your data, there might be different layers that are worth exploring. But let's just take a look at the last 2 layers. So layer -1 will give me the last layer. Then the name of that is predictions. And then the second to last layer, average pool. So I know that the names of my layers that I want to grab are average pool and predictions. I can grab just those layers by saying net, give me the layer, and I have to give it the name. So I'm going to ask for the name, and then I want the output of this layer. So this is pretty obscure code. You'll just have to trust me that I had to look up some documentation to figure this out. But then now you have it, so hopefully you can use this as your documentation. So this will grab the layers that represent those 2 layers activations. Then we can create a new model, just like this is a model. It works in the same way. We're going to create a new model by creating a Keras model. We're going to give it as inputs the same input that our previous network had, so an image. But instead of having just one output, we're going to have our new layers as outputs. Cool. So that's just some maneuvering to allow us to actually get features out of this network. Okay. So yeah, as I mentioned, each layer has really different properties. So we could explore different layers if you want. I'm just going to grab an image here. This is just some code to grab an image from this Python module of an espresso cup. So you could grab your own image, or you can use this as a test if you want. How do we now run this image through our neural network and get our features as well as the predictions? Well, I mentioned that we could call this model. And what I meant by that was we can actually just say, let's say activations equal model, and then I give it the image. It's almost as simple as that, except it'll complain. It'll say, you have to be 4 dimensions, but you're only 3 dimensions. Your image is 400 by 600 by 3, but I need 4 dimensions. And so the 4 dimensions that it needs, the fourth one, is the number of images. And we saw last week when we created our mean that the 0th dimension represented the number of images. That's what it wants again. It wants that same type of representation where you have the number of images, then the height, then the width, and then the number of color channels. Pretty much every image neural network works like that. So we could try to find another 99 images or whatever, or we could just create another dimension on this image, which is just sized 1. So one way of doing that is saying numpy new axis. And so the shape of this image is just created a new singleton dimension. It's basically saying create a new axis in the 0th dimension. We could have placed that new axis somewhere else. This is just demonstrating what this thing does. So we could have put the new axis there, for instance, and it'll appear there. But this won't work still. It'll think that you have 400 images with 600 rows in 1 column, and that's not right. So we want the new axis to be here, and this represents the number of images, of which we have 1. So this will still almost work. If we try this now, I should save this as the image. So I've got activations, but it's not actually correct. This model in particular requires a pre-processed image. And it's pretty arcane. Like, you should dig into the Keras documentation of the implementation in order to know this and figure this out. But just trust me when I say that the way to call this neural network with 1 image is to have this this function here, this preprocessed input, act on a float image. And so our images min and max here were 0 to 255, and we're not rescaling it when we create a float image. And we saw last week that float images have to be between 0 and 1, whereas here the float image actually has to be between 0 and 255, and then preprocessed. So it's a little weird, but this is, if you get this process, then you can run a neural network with inception with 1 image like this. So that will give me the correct activations. And we can take a look at what's inside of here. Lots of numbers. I've got one tensor array, same thing, shaped 1 by 2048. So there's one image, so there's one set of activations, and there are 2048 values. That's that average pool. That's that feature layer. That's what we're trying to get at. And then there's another set of activations which have 1,000 values. And those are our predictions. So we can download the labels for each of these 1,000 predictions and take a look at what they represent. Like for some reason, it thought whatever this 0th label was, it gave it a 0.001, like a point, yeah, I have to do my math in Python only. So it gave it a 0.1% chance that whatever that image was, the espresso cup, it thought with 0.1% chance it was that label. And so on for all these other labels. And the sum of all of these values adds up to 1. So let's try and download the labels for each of these indices. And that's what this network was trained on. And we'll see what it thought this image was. So these are the labels, the 1,000 labels that each of these probabilities represent. So the 0th label was a tench. What's it? I don't even know what a tench is. I feel like it's a fish because it's next to other fishes. Anybody? It must be some fish. I don't know. Well, it thought it was some type of, oh, I have an internet access. I can just ask Google. There you go. It thought with 0.1% chance that the espresso cup was this type of fish. Cool. Let's see. So the last, our activations, remember there were 2 tensors inside of here. So let's just grab the last one. I can ask for the last by going from the end and then going back 1, or going from the start and going forward 1. It's the same index. So let's call this predictions. And then what are our predictions really? So this is a TF tensor, but inside a TF tensor, there's actually a NumPy array, which is what, it's a more friendly format. That's what we'll actually use. And we can ask for that data by just saying .numpy. And that will actually give me a NumPy array instead of a TF tensor. So let's call that preds. And then let's find the predictions that have the, I'm going to plot our preds just to take a look at what these are. Oh, wow. That plotted 1,000 lines, which isn't what I wanted to do. I can transpose this so that it is 1,000 by 1 instead of 1,000 by 1. I'm going to plot it using matplotlib, but I just want 1 line, not 1,000. And so on the x-axis here, we have the values of each of our 1,000 floating point values. And then there's some label here, which is really high compared to the others, at least. It's still pretty low, about a 10% chance, let's say. And then there's some other label here, which should give some extra probability to, but how do we get the index of this very large value here? We could probably go looking for it, but with code, is there a way that we can ask for this array's maximum value? maybe we type in dot and see what happens. Are there any functions in here that might be useful? In order to get the index of the maximum value, there's this notation called argmax. And so we basically just write argmax. And that will tell me the index. Same thing for min. So if we wanted to know the min value, we could ask for the argmin. And that's the index, which had the minimum value. So pred of 967 should equal, oops. Let's see. The 0, because our predictions are shaped 1 by 1,000, I have to get the 0th dimension of that one-dimensional axis, and then the 967th value is the maximum value. So I've downloaded my labels up here, and this is a list of 1,000 values. So if I look up the 967th label, I should see. Any guesses? It thought it was an espresso, but it was right, I guess. I mean, maybe it could have guessed saucer or table or spoon or any of the other things, but mostly right, I would say. So we've seen how to do this prediction for one image. We've got a neural network. We ask for specific layers. We downloaded an image. And then we had to do some transformations on the image here in order to ask the model what its activations of that were. And then we grabbed our predictions. We haven't touched these features yet, but we looked at the predictions and downloaded our labels for each value of that prediction array and saw which index had the highest activation and saw that it was the espresso label. So coming back to this visualization, we've basically looked at this last layer and we've seen the 967th neuron was espresso. So we've gone through this process here. Yeah, so you can convert between a float image and a uint8 image as you want. The important bit is that the min and max should be between 0 and 255. And then the value that you give it have to be has to be between 0 and 255 as a float. So if your image is stored somehow as a float image, and you see that the min and max are 0 and 1, then you should scale it by 255. So if the min and max here aren't 0 and 255, scale the image so that it is. So, and you can scale an image just by multiplying by it, right? So this would, if my image were 0 to 1, I could rescale it so that it's 0 to 255 by just multiplying every pixel value by 255. And then if your image is RGBA, you would want to ensure that you get rid of that alpha channel. Otherwise, it'll say, I don't know what to do with that extra channel. So you could write here 3, and that would remove any alpha that was in your image. So in the notebook, that I'll share, I have two other examples of running this process, but with 100 images, and then with another data set that have many more images, and then I apply it again to 100 images. I'll let you take a look at that in your own time and just go through that process. So what I want to look at now is moving on to extracting image features, which we've already done. We've done it for one image, but I want to do this for a lot of images now. And that will get us set up to start looking at dimensionality reduction of those images and seeing what a neural network thinks is similar for that set of images. So we've been working with this image data set of faces up until now. I'm not too confident our image classifier will know how to distinguish different faces. It won't be as interesting. This network was trained on the ImageNet dataset, which are many different objects. So I don't really have a data set of different objects handy, but I do have some weird videos on YouTube, and I can download one of those and try and extract still frames from that and see what a neural network thinks of that. So this is a video of a GAN, effectively, like a style GAN that we'll look at in a couple of weeks. And this was done with Rafiq Anadol's studio and used that 20-some terabyte collection of images from the LA Phil archive. It was pretty interesting generation content. Maybe let's look at it just quickly to give you a sense of what's in here. There's just weird stuff, basically. So there's not really objects in here, but there's a pretty good variety of different things happening, and it's quite abstract. So I guess it would be interesting to think about what a neural network thinks of this. It was never trained on abstract images, so let's see what it thinks. I'm going to now, as we did in the last session, I'm going to use this ffmpeg command to dump out a bunch of images from that video. I'm giving it the frame rate. I want a image every 2 seconds, and I'm also going to scale the images so that the width dimension is 512. So once this is done, I'm going to load up all the images as we've done last week. I create a glob. I say I want anything that matches these PNG images. I'm going to just load 100 of the images because I don't want to work with too many images just yet. We'll look at that in a bit. And then I'm going to just produce some useful information about my image array. So I'm always mindful, like, this is a issue with neural networks. I always have to find out the right type. I have to make sure they're scaled between the right min and max, and have to try and check their shape as well. All right, so I've got now images that are scaled between 0 and 1. They're floating point. And I've got 100 of them. The shape looks okay, but the min and max look wrong. So we mentioned before that they have to be floating point values between 0 and 255. And that we can just scale it in order to get back to 0 to 255. So that's what I'm going to do. You can also give it uint 8 images between 0 and 255. That's also acceptable, but yeah, so the range basically just has to be between 0 and 255. If you've loaded a float image, scale it to 0 to 255. If you've loaded a uint8 image, then great, you're already set. If you want to, you can treat that uint8 image as a float as well, but then don't rescale it. So if your images are floating already, rescale it to 0 to 255. It's basically the case that you have to look out for. So just like before, we had a bunch of images. We only had one image, sorry, and we called this preprocess input function, calling the model after that. We don't have to create a new axis this time because we actually already have 100 images, but we do have to scale it by 255. Okay, so that should do what we want it to do. This will take a little longer. If you want it to take slightly less time, then you'll want to be sure that you are on a GPU runtime of COLAB. And this COLAB is on a GPU runtime. In order to change to a GPU runtime, you would have to restart your notebook and go to runtime, change runtime type. And then for hardware accelerator, go to GPU. So I actually wasn't on a GPU. Well, I won't restart now, I think. Just keep it as is. Let's see. So we've got our activations. We've got features, again, in our 0th. Oh, sorry, this one. This will be a really large amount of numbers. Let's see what happens. Okay, so they clip it for us. We've got 100 activations of 2048 features. And then we've got 100 probabilities of 1,000 different classes. Okay, so we could look at, for instance, the labels of every image if we wanted to. I'm not as interested in that. I just want to explore these features first. So we saw last week how to use the mean to sort images, right? We used the mean pixel value. And that was a pretty powerful representation for a data set that was very, very constrained, the faces. There was only deviation really in the parts of the image where there was a lot of change in the face, and then also in the background, but you got a lot out of the mean standard deviation with such a constrained data set. And as some of you saw in some of your exercises, the more constrained that data set was, the more helpful the mean was. Well, now we've actually got a really good representation. So we could use the mean here and try to look at what is the representation change across our mean activations, and what's the standard deviation of that. That's one way that we could look at sorting our images, and that'll give us one axis, one dimension. So let's take a look at that, because we've already seen how to do that. We would calculate the mean of our features. Well, let's first grab the features. We'll say features, activations. I want the first activation, so the 0th activations. And then remember, this is a TF tensor, and I want it as a NumPy array. So I'll say .numpy. So I've got my features, and the features are 100 by 2048. you know, just for fun, let's look at this as an image. Why not? What happens? There's not much to look at, really, you know. Fine, okay, it was worth a try. Nobody knows how to interpret these features, basically. They're a bunch of numbers. That's why we're going through this whole process of trying to reduce it down to an axis, which is more meaningful, or with t-SNE later to a set of two numbers where the two numbers represent how similar images are to each other. Okay, so let's calculate the mean of our features, mean features. We can say np.mean features, and we want this across our 100 features. And then let's collect the distance of every image's features to our mean feature. So this is more or less the code that we've seen before. We're going to go over every single feature. I can write a loop like that. This will automatically index the first dimension of my features. And so this will be 1,000 values each time. And I can look at the distance between my mean feature and that element. So I could say that'll be 1,000 distances. Every feature's distance with the mean feature distance. Oh, sorry, 2,000 values, 2,048 features. And I could even look at the mean of this. So that's really what I want, is like one value that I can now then use to sort my images back into a montage, just like we've done before. I'm going to calculate the mean distance of every feature with my mean of all of my features. And then I'll store all of these in the same order as my images. And then I'll sort my distances so that they're in order of the values of those distances. So I'll get indexes equal to the arg sorting of my distances. Just out of curiosity, what do the distances look like? It's a bunch of different values. Some are quite close to the mean. This one is quite far away from the mean. This one seems much closer. So the sorting has taken all the distances and organized them so that the distances are now in order. And so if we try to use that same order and look at the order of our images, that should hopefully preserve some sense of features of those images. That's one axis of our features space. Okay, so we can sort our images. We'll call that our sorted images by indexing every image for each element in our lookup table, effectively. These indexes that we've just created are the indexes that sort our distances. We're going to use the same indexes to sort our images now. And then we'll create a montage out of our new images. And this needs to be an array. We've seen that code before. And then we'll draw our resulting images. Let's draw it large. Let's see. Okay, so let's manage to find all the title frames and the blank frames. And there's some sense of similarity going on, like the maybe busier stuff is happening later, and like well, this one's quite busy. I'm not totally sure it's done something really obvious past this clustering of really different material from the rest. But this is just one axis of that feature space. So how can we really take advantage of all 2,000 some dimensions of these features? So that's what we're going to do next with our image dimensionality reduction methods. We're going to look at TSNE and PCA and UMAP and see how we can take those 2,000 some features and then project it into a two-dimensional manifold. Whereas this is a one-dimensional manifold. We're going to now try to organize it into 2 dimensions. Using the same method, we could even project it to 1 dimension, or 3, or any number of dimensions. So you'll find a couple links in the COLAB that is on the course website. And they will describe this TSNE algorithm a bit more, but they go into a lot more detail than perhaps you'll want to know. But they're there for you as reference if you want to look at them. What we're trying to do is take, so this says 1,000, but just replace this with 2,048. So our features have 2,048 dimensions. And we know that somehow the neural network likely have similar features for similar looking images. And we want to try to understand its idea of similarity. What does it think is similar? And we want to try to take these 2,000 some dimensions and reproject it into 2 dimensions, such that the distances in the high dimensional space, the 2,000 some dimensions, if things are far away, then in our low dimensional space, they should also be far away. And if things are really close in that 2,000 dimensional space, they should be really close in our 2-dimensional space. So that's the idea. We can play with 3 of my favorite algorithms for this, PCA, TSNE, and UMAP, pretty easily inside of this package called sklearn. There's an algorithm for PCA. There are many types of PCA. This one called incremental PCA is actually quite good with really large data sets. So that's the one by default I just use all the time. TSNE needs no introduction, I think, so far. And then UMAP is a more recent technique which builds on some of the findings from TSNE, but addresses some other issues. It's purely aesthetic, I think, at this point, what you end up using. But UMAP has some really fun new features, which we won't be looking at today, but if you dig into this in the future, remember these words to revisit UMAP because it has some really cool tricks like reprojection and supervised and semi-supervised learning, things like that. Okay, so we import these, and the way that these work is that we're going to give it our 1,000 dimensional data. And each, these are classes, class come across classes in other languages. They are containers for defining objects, and objects can define functions. So we're going to instantiate our class, and that will create an object. So we can kind of try to inspect what that means a little here. So we've got incremental PCA. It's saying here that this is inside of this module. It's a class. That's what that means in Python. We create an instance of that class, also called an object, by passing in the parameters that it wants. So there are a lot of parameters for each of these. The only one that we're going to look at is this number of components. So how many dimensions are we going to use for our dimensionality reduction, essentially? By default, these are 2 already, I think. I know it's not for PCA. So we'll set this to 2 for each of our methods. And this will create an object. We can just call it like a little PCA, for instance. And then inside of this, there's going to be a function called fit transform. And all of the, well, practically all of the sklearn methods use this methodology where they have a class, such as PCA. You'll create an object, and then you'll call this function fit transform in order to apply the algorithm to it. And so UMAP also adopts that same methodology. As input, it wants a NumPy array, which is the number of observations, the number of samples, like how many images, for instance, we have. We have 100. We have 100 samples. And then the number of features. So our second to last layer of our neural network has 2048 features. So we actually already have this parameter. There's this other optional parameter we won't be using. So we give it our features, effectively. What did we call our features? Features, okay, cool. So our features are 100 by 2048, which is what it wants, 100 by 2048 features. So if we give it our features here, and let's call this X new if they want, fine. You might find that you always see these letters X and Y. Like, why is that? Always in machine learning, why is it always X and Y? X somehow became the representation for an input or your data, let's say, and Y always became the representation for a class label, or often the output in a supervised network. So that's why that's there. It comes from probability notation. So it's basically saying, like, what's your data and what are their labels? So we don't have labels, we just have our data, and we're going to transform our data so that it is now been transformed by PCA into a new shape representing the same number of samples, but now with a new dimension from 2048 to 2. So let's call this features 2D. And now what? We've got our features in 2 dimensions. We can draw this as a scatter plot. That's one way to kind of look at this. So Matplotlib has a method for scatter plots, and it takes the x-axis values and the y-axis values, and it will plot points, basically. So we could say our features 2D, every single observation of the first feature, and then let's look at every single observation of the second feature. So that is our dimensionality reduction of our image data set. The only problem is I have no idea what each point represents, like what image is it. I have a pretty good idea of what these are. These are probably the title screens and the dark screens. These here. But what I really want to know is how does this neural network think the rest of the images are similarly similar? So I did a Google search, basically. Let's see if I can do the same Google search. Matplotlib, draw images as scatter plot. And maybe it's this one. Yes, I think, no, it's not this one. Okay. There was another Stack Overflow. Draw images as 2D. Maybe images as 2D scatter plot. Well, of course I can't find it now, but you'll just have to trust me that somebody on the internet figured this out, and then I copied the code, and this is the code. So there was basically a way to draw an image at a given point using this annotation bounding box. And that's the code. I wouldn't go into too much detail on what this offset image or annotation box do, but there are parameters that are fun and useful. So one is that you can actually rescale the image. You can also apply alpha to the image. This is really pushing the limits of Matplotlib, really, because it's, it's not the best visualization library, but I shouldn't say that. It's pretty remarkable for what it does, but if you're more comfortable in another coding language with visualization, you have a set of points now. You have a set of 2D points, and you have a set of images. Maybe there's another language that you want to use that is better at visualizing images, like P5 or even like Houdini or C4D. I don't know if you're familiar with those tools, but that's how you can start to get like some really cool things happening with this workflow. So let's take a look what happened to our images. So we've got some dark images in the title screens here. We've got some maybe like single person, two-person images going on here. Some outdoor stuff here. Yeah, we didn't get the alpha, in fact, because there's a sneaky parameter here, which is frame on, which should be false. And that was a really weird parameter to try and find. But now we can kind of see where there's more density of images. Like this is pretty collapsed onto a point. There's a pretty strong overlap there. And yeah, there's something happening here. So this is PCA. This is just one algorithm, but we do have these other algorithms available. let's try and repeat the whole process, but with tsne instead, and try and compare. I'll call this one tsne. Let's actually do something more clever, slightly, and do this. We'll calculate all of them. Do this for tsne. Okay. So all of these will be shaped the same. We'll just set one of these equal to features 2D and take a look. Let's see the tsne. Some more spread here happening. And definitely learn to disentangle that mess a little better. Let's see what happened. Okay, I see a whole cluster of concert stages that I didn't see before. This looks pretty nicely clustered and feels like a visual cluster to me that I would probably have grouped, maybe. All the two people faces here nicely clustered. So it's pretty interesting that this was a totally abstract data set, but it still knows enough about the structure in that image to somehow find structure in it. And there would definitely be failure cases because this is a algorithm at the end of the day. It's not like a silver bullet. And it's interesting to try and find and identify those failure cases. So let's take a look at UMAP now, the last one. Oh, so it really was like, those are very different. And let's see. Okay, so it's even got all the blank images here, but the title screens are mixed in here with something that's definitely not a title screen. This is actually like a screenshot of a Windows thumbnail gallery of a bunch of images. Don't know how that ended up in the database, but there you go. There's this really scary face here. Yeah, let's say that there's peculiarities of each algorithm. In general, aesthetically, I find the tsne often the most interesting. But have a play with it. And each algorithm have parameters. PCA, there's nothing really to play with, but for tsne, there are two parameters, the perplexity and the number of neighbors. So these two values are really interesting to play with. And in this article, you will find some explanation on it for different ranges of values, so different perplexities. And yeah, you only look at perplexity, but you should also look at the number of neighbors. Okay, yeah, they only look at perplexity, but also looking at the number of neighbors is interesting. So they have a default. Oh, so sorry. This is the value perplexity, and the learning rate would be the other interesting value. And they give you a range of different values to explore, and that article as well has different steps, which is the same value basically that they're exploring. So you can experiment with those two values by just saying like perplexity equals 10 or 100 or 1,000 or 1, the different ranges of values, and kind of use this article as a guide if you want. And then for UMAP has neighbors. I think that's UMAP have the number of neighbors, which defaults to 15. Give you a range of values that you could try between 2 and 100, and same for number of components. So those will lead to pretty different aesthetics, things you can do with that for sure if you work that into your practice. Okay, there's one last thing that we're going to look at, and that is how do we use this reduced down representation, which represents 2 dimensions, and reorganize it so that it fits into another set of 2D points. So let's say I want this to look like a grid. I want, to somehow stretch these images in the top left so that they are all in the top left of my grid, and that these title screens are in the top right of my grid, and like this stuff happening down here is on the bottom left, and so on. Or maybe I've got another set of points, like a sphere. I want to create some weird animation that, rotates around globe or something. Or maybe I've got an image of continents, and I've got points that represent that thing. Or we saw an example, did we see this example of Toralba, for instance, had like a bunch of images plotted on the globe. And there are examples of people like plotting the political views of different senators on a hourglass or something like this, and split down the middle, and they find some feature of each senator and try to find the similarity between them using this T-SNE algorithm, and then reorganize those points into something that looks like an hourglass. So there's a lot of potential graphically to kind of play with this technique if you feel comfortable with it enough and have an idea that you want to explore. But let's take a look at this problem. So I mentioned before that this is known as the assignment problem. And there are different solutions to it. The one that we're going to look at is called the Hungarian algorithm. And I don't know why they call it that. But there we go. So what we're going to do is a bit of strange code just to create a grid. So, if you had already a set of points, you wouldn't need to do this, but what we're going to do is basically create a set of points that represent a grid. Right now we've got a set of points that represent our 2D features. They look like this. And what I want is just a sampling of points in a similar range, but I want a sampling of points that represent a grid around these points. So I've already done this, and the way that we're going to do it is create a set of points that are around the range of our features. So this linspace operation is basically saying, look at the min value of our features. So the min value of all the features, X or Y, was -4-ish, let's say. And then scale that by 2. This is totally arbitrary. So now we're going to have a grid that starts at -8. And then look at the maximum value. Okay, the maximum value was on the x-axis about 0, on the y-axis like 15. So we're going to get 15 times 2, so 30. So we're going to have a grid between -4 and 30. And then we're going to take the square root of our images. So that will give us a sensible number of grid points on our x-axis, and our y-axis is going to be the same range and the same number of points. And we're going to use this mesh grid function in order to create our new x and y values. So you don't have to create a grid like this. You could create it manually if you wanted, or I'm not sure how else you would play with this, but you could export, for instance, a shape file that had a set of vertices, and you wanted to use those vertices instead. And Python can read shape files. You could probably find some information online for how to do that. So this is just an example of using a grid. Our set of x's and y's are now in this mesh grid format, and this is such a wild function. It's such a weird one. I always struggle with it, but it returns what's called coordinate matrices, and I really don't understand them, to be honest. But in order to transform this into an actual set of points that represent our grid, we're going to use this stack operation. So our x's are in this really funky format. We've got for each row in our mesh the x values, right? And so these are all the same x values of our grid. So that would be, minus 4 times 2-ish, so minus 8. We said it would go up to about 30. We've got our 10 values, which is the square root of our number of images. And we've got our x values going along the grid here between minus 8 and 30. And we've got this 10 times. And for the y's, it should look identical, but going up. So we've got the same y value for every x, and then we've just got sets of those y's. So that's what this mesh grid function does. It always trips me out. But we need our set of points to look like our features set of points, right? Like each xy value as a list, basically. So we can do that using this dstack operation, and that will stack the values along a new dimension. And we've got now all of our xy values as a list of points. Okay, and I can draw this as a scatter plot, as I've done before. I've got all my grid points. Right. So that's all we've done, really, is we've created a set of points. So in the notebook, I show here basically what our embedding looks like and what we want it to look like. So what we're going to try and do is find the point on the left that should be assigned to the point on the right. That's the assignment problem. So in order to do this, we're going to create a set of costs using a function called cdist. This is just a way of calling a lot of different distance functions. And we're going to call the square Euclidean distance function. And we're going to optimize this algorithm, which SciPy provides, called a linear sum assignment. It's an implementation of the Hungarian algorithm. And this will give us a set of indices, basically. So this is pretty complex, but you can pretty much treat this as boilerplate. You give it one set of points and another, you calculate some cost that measures the distance between every grid point and every feature point. And then this is trying to find some assignment based on all of those different distances, and will give you the indices that sort your features into the ones that represent the same sorting of these grid points. So a way to visualize this is we can visualize the features based on these returned indices, and I'll dig into this in a little bit, but let's look at what it does first. Did I not call this? Okay, so what we're doing is this will return the set of indexes for that map each set of points that we gave it. So for the indexes in our features, for each feature, for the ith feature, what is the index that maps to that same ith grid point? And we're just drawing a line between each feature point and each grid point. So if we want to sort our images now on this new set of indices, we've seen how to do that with our mean indexes that we've sorted before. We're just grabbing the first dimension here of that indexes array instead. So we would look inside indexes of 1. These are the indexes that correspond to the grid points in the same order. So the 0th grid point should be the 83rd image. The 71st image should be the 2nd grid point. The 87th image should be the 3rd grid point, and so on and so on. So we can sort our images again by saying, give me each element in that indexes array, and I will sort my images using those indexes. And then we can do our montage, which we've done a couple times now. Images sorted. All this. And this is our grid, basically, now been assigned to by this assignment problem. And we can use the previous code, which was a scatter plot, drew it on like a grid. And this will still look like a grid because, you know, all the images are on equally spaced. But whereas before that code drew this, we've now mapped that to a grid here. The X and Y's are probably flipped. But, all right, in the notebook, I've gone over one last thing, which is loading a larger data set. And it's not required of your homework or anything. It's just there for you in case you're interested in that. It involves one extra technicality, which is when we calculate with the neural network, when we project our images with the neural network and try to find the activations here, we gave it all of the images. 100 images. That's fine if you've got 100, maybe even like 200, but at some point you'll run out of memory. And so the code in the notebook basically gives you a bit of boilerplate, which looks like this. And it does what's called batching. And it will produce basically the same result as this, but allow you to work with much larger sets of images. What it's doing briefly is taking 100 images at a time, projecting it through the model, and then storing those activations. So generally, that's a good practice if you don't want to lose memory, run out of memory. That's in the notebook that's shared online and explained a little more as well with some context. So with that, your homework is to extract features using a, well, I've got this in the keynote. Basically, you will have to extract features using a neural network and create a low-dimensional scatter plot of your images. And then you'll have to reproject your images using the assignment problem. And then there's a lot of optional things that are, in case you want extra credit and feel challenged, this will push what we've seen in the lab towards some new directions, such as assigning to something other than a grid, or exploring a visualization in 3 dimensions. And you don't have to use Python for that, but you would use Python to get the coordinates of your 3D space. You could also explore animations of the grid, such as like starting from one clustering or one scatter plot basically and going to another, or one assignment problem and going to another assignment. And then this last point of adversarial images is basically trying to get you to think about failure modes of the neural network. And we've seen how to load up this image neural network. You could do some research on what images it was trained on and try to find images like that might not be well represented, and try to see what it thinks of those neural networks. What it thinks those images are predicted as. And that would be an interesting exercise as well. So that's it for today. Are there any questions or concerns? Let's use this package called pandas. So you can import pandas as PD. It's a common way of importing it. Actually, I think you can even just save this as a text file, but okay, let's try pandas. So PD provides this thing called a data frame. And I believe you can just give it the NumPy array. Yeah, it likes that. And with the data frame, you can write this, I think, as write CSV. I'm reaching. Let's save this as df data frame and see what PD has. Write to save df dot save right CSV PD CSV. I have to search. Right CSV. I swear I tried that. GF2 CSV. Okay. And then you would give it the name of a file. So features.csv. And there's options, like if you want to use a different separator, by default it will use commas, but you could use like tabs instead. By default, it will separate each value by a comma. If you want to give it tabs, you would give it \T for tab, or a space, and that would also work. This should output a file like this. It's being drawn as that, but it's not like that. Let's see. Of course, it's opening it in numbers. That's not helpful either. Let's see. Okay. This just looks like this. So if this isn't the format that Unity wants, you can also export this as a JSON file. You can also step through each line in the features and create a file. So let's say with open a file, we'll call this features 2d.text. We're going to open the file in write mode and then create a variable with this context manager. And we'll basically write each line of code, each line in this features array. So for feature and features 2D, we would say fp.write in order to write into that file, and we could write each feature value. So we could say, there are many ways to format strings in Python. One that I like is this format string, and you create a format string by saying f and then a string. And what that allows you to do is create a string using variables. So I can actually just write the variable inside of here, and that will create a string out of that variable. So that would create a set of numbers, and then I could create a new line at the end, for instance. That might do something useful. You could write each individual feature, maybe with the comma as well. Feature 1. That would be another feature output. That might be something that's easier to parse. You can write JSON files. So with JSON, you can use the same ideas as this, but create a JSON file now. And you would write JSON.dump. That will expect an object and then a file pointer. And you can create the object from a NumPy array by saying JSON.dump as string dumps the NumPy array. That would be, so then we would say to list first. So we would convert our NumPy array to a list, and that's already JSON friendly, but this would basically ensure that that is JSON friendly, and then we would write that instead. So that would look like this. I think that's pretty much covers all the ways you might want to export. I'll add this to the completed COLAB. And I'll share this. We already have this one actually shared, but I'll ensure this one's also shared. Any other questions? Well then, we'll see you Tuesday, same deal. It's been a pleasure. Thanks everyone.